Every year, millions of students sit down in an algebra class, look at the expression x plus y squared, and inevitably write down x squared plus y squared. Since this mistake appears consistently across different countries and age groups, the problem likely lies in the design of the notation itself. The technical term for this is hidden state. It occurs when a system's behavior depends on rules that are entirely invisible to the user. Standard algebra is a human-made user interface, developed over centuries and packed with these invisible rules that have nothing to do with the underlying math. For generations, we have wrongly diagnosed a failure to navigate a bad interface as a lack of student intelligence. In this interface, writing a 2 next to an x requires the student to know that a multiplication sign exists in the empty space between them. In the previous chapter, that same visual layout meant something else. A 2 next to a 3 indicates 23, a place value relationship, not 2 times 3. This inconsistency leads to the fruit salad error, where students read an expression like 4a plus 3b as 4 apples and 3 bananas. These students are applying standard real-world abbreviation rules to an interface that fails to display its own variables. Their logic is sound. The display is underdetermined. When a system's meaning relies on context the screen refuses to show, novices are forced to guess. Math becomes a wall of memorization. Historical notation was shaped by the physical limitations of paper. On a flat, static page, a single set of symbols had to be easy to write, easy to store, and easy to compute with all at once. Standard linear notation became the dominant standard because it could be scribbled quickly and took up very little space in a printed textbook. To fit an equation onto a single horizontal line, mathematicians stopped writing out every operation and invented invisible hierarchies, like PEMDAS, just to save horizontal space. These confusing conventions are baggage from an era when saving ink and parchment was the primary goal. In 2004, David Kirshner and Thomas Outry tested whether changing the visual shape of an equation could eliminate these systematic errors. They utilized tree notation, expanding the symbols into a two-dimensional layout where the primary operator sits at the top node. This layout makes the hierarchy explicit. You see the physical connections between operators and their arguments, removing any ambiguity about what applies to what. When students used this spatial interface, their error rates plummeted. Students calculated correctly because the interface finally reflected the mathematical structure they were already trying to navigate. While tree notation clarifies the math, it takes up too much physical space for experts to use for long derivations. Digital screens sidestep the historical constraints of ink and page margins. Software innovator Warren Robinett proposed a morphing algebra environment to address this tension. This uses the parallel alternative principle, allowing an equation to exist in both a compact expert view and an expanded beginner view. If a student hits a confusing expression, they can literally click the notation to pull it open into an explicit tree view. After checking the structure, the expression snaps back into its compact form so they can continue working at speed. Modern software can bridge the gap between human intuition and symbolic logic, letting students see the structure of math before they are expected to master its shorthand.